Hello, so continuing on this Leetcode weekly contest 171. So the third problem was number of operations to make network connected. So what the problem says is we have n computers numbered from 0 to n minus 1, and they are connected by some Ethernet cables, connections forming a network, where a connection, when we have a connection at position I is A to B, means that there is a cable connecting A to B, computers A and B, and then any computer can reach any other computer either directly or indirectly through the network. So for example here 0 can reach 2 by going either directly from 0 to 2 or 0, 1, 2. And then given an initial computer network of connections, you can extract certain cables between two directly connected computers and place them between another pair of disconnected computers to make them directly connected. So for example here we have this cable connecting 1 and 2, but 1 and 2 are already connected via 0 here. So we can just move this cable over here and connect 1 and 3 with it. That way we can make the entire network connected. And so the problem asks us to return the minimum number of times we can do such operation, where we get a cable out from a redundant connection, right? Because connecting 1 and 2 here is redundant, and we connect to that one connected 1 and 3. So the minimum number of those that we can do, we need to return it. If we can't connect the entire network using this, we need to return -1. And so there are the other examples are very similar. And then the boundaries, n is all the way to, it can get to 10 to the power 5. Connection length, same, almost similar thing, it can get there. And then, so the bounds are kind of big, so we can do an overfit squared solution definitely. Okay, so now let's see how we can solve this problem. Okay, so let's see how we can solve this problem. So if what the problem said is that we want to find the extra cables basically, and then we want to see if those are enough to connect the entire network, and then are they enough to connect the entire network. Basically not really are they enough, but how many can we use to connect the entire network. To connect all computers essentially. So they can be more, that's fine, but if we can't, if it's less, the number of extra cables is less, then we need to return -1. If we can't, we need to return -1. So if we look at this, then we need to we need to find the number of extra cables. So that's like the first step we need to do. So find the number of extra cables, and then after that we need to find the number of unconnected computers, right? Number of unconnected computers. And then from there we can just check if number of extra cables is less than the number of unconnected computers. That means we can't, right? That means we return -1. Otherwise, which means there are enough extra cables, then what should we return? So we know the number of unconnected computers. So if you have, let's say, 3 unconnected computers, or maybe it can be like these are connected, right? And this is maybe with another one. So these two are connected. So to connect these 3 together, what do we need? Well, we need a link between these two. So once we put this link, it became connected with all of them. And then we need a link either between this one and this one, or this one and this one. So we need only 2 links. So for 3 components, we need only 2 links. And that's basically a general case, right? Like for n components, to connect them, we need n-1 edges. So here, that means we need to return components -1, right? Number of unconnected components, which is just the number of components actually, right? So it's just components -1. Return components -1. And so how can we do this? So finding the number of components here, we can do that with union find or disjoint set, right? So we can do it with a data structure called union find disjoint set, right? And so also we can find it with DFS, but for this, if we use union find, we can find the number of extra edge cables by doing union find. Let me explain why. So let's see if we have, let's take an example. So for the 0, the first example that we had there in the problem, so we have 0, 1, 2, and then we have 3 here. We had links between 0 and 1, and between 0 and 2, and then we have an extra one here, and then we have 3 not connected, right? So when we are doing union find, first we have these here, right? We have 0, and then we have 1 as a component, and then we have this as a component. And the parent of 0 is just 0, the parent of 1 is just 1, and the parent of 2 is just 2. Now we go through each connection, so we go through the connections in order to union them. So we will have to write union and find, but for now, let's just suppose we have union that can union 2 nodes. If you are not familiar with union find, I suggest that you look that up first, but it has this one that can union 2 nodes, and then we can have find that finds the parent or the representative of the set, and so for a node. So we have these 2 functions defined. Now we will need to go through the connections that we have. So for every connection, these are the 2 edges in the connection. So what we need to do is we will need to get the parent for each one of them. So the parent of U would be finding the parent of U, and PV would be finding the parent of V, right? And so now if both are in a different components, which means that their parents are not the same, so basically being in the same components means their parents are the same here in this union find framework here or context. So if both parents are different, that means they are, so there is an edge between them, but they are not yet in the same component. So we need to union them so that we put them in the same components because they are connected, right? So if you have something like this, and then you have this, and you already set up the components for this, well, this is part of the component as well, so we need to include it. So that's why we do union of U and V. Now, if the parents are already equal, like the case here, so if once we do this, so once we, let me just get this back. So from this case, once we union 0 and 1 because we find an edge between them, what do we get? We get something like this, 0, 1, and then we have 2 here, and then we have 3 here still. So, well, we have now this component, right? Because we union them. And so 0 is, let's say we choose 0 as the representative. In the step after that, what will happen is that, well, now we also find the link 0 and 2 because we are traversing the connections. So now we would have 0, 1, and then 2. And now we have this entire thing as a component, right? And then we process the link 1 and 2. But now, if we will find that the parent of, when we do find for 0, we are processing the link, so processing the link 1, 1, 2. So what we will find is that find of 1 is equal to 0 because we already put them in the same components, and then find of 2 is the same, it's 0, 2, right? So that means they already are in the same components, but there is still an extra edge between them. So that means we found an extra edge, right? So found an extra edge. Because they are already in the component, in the same component, and we find another edge that connects them. So here, in this else here, that means we have an extra edge. So we need to initialize a variable here that keeps track of the extra edges, and we need to increment it here. So you can see here with union find, we can both find the number of connected components and we can find the number of extra edges. And so once we do this, how do we know the number of components? So in order to find the number of connected components, we can just get the So in order to find the number of connected components, we need to get we can just do find again, right? So we can just take the set of the find u. So this will give us all the parents, right, for u in the range of n, right? So this will give us all the remaining, so it will give us all the parents of, and then that would be unique because of the set. And now we'll get the length, the number of components, by just getting the length. So this will give us the number of components. And now, how can we know that we have enough to connect? So now we found the number of extra cables. We know the number of connected components. And the number of connected components is just the number of unconnected parts, right? And now we need to do the check, right? We can just check if the number of extra cables is less than the number of connected components, we return -1. Otherwise, we return the number of components -1. So we just do if extra edges are less than components -1, then we return -1. Otherwise, we return the components -1, right? And that's all there is to it. We will need to define union and find according to union find data structure like implementation. But essentially what we will be doing extra is just going through the connections, connecting everything and putting everything in a component that is already connected. And then if we find that there is an edge that connects two elements or two nodes that are already connected, then that's an extra edge, so we count it. And when we do the union find for all the connections, we now know the number of components, and we can just do the extra, check the number of extra edges if it's less than the number of components -1. If it is, that means we don't have enough extra edges, so we return -1. Otherwise, we need to return what we need to connect the components, which is just components -1. Okay, so now let's just write this in a more organized way on Leetcode and see if it passes the test cases. Okay, so now let's write this on Leetcode and see if it passes the test cases, right? So the first thing we need to do is write our union data structure, right? So we need a find for a node, and we need a union that unions two nodes, u and v, or let's call it x and y, right? And then we need, so the nodes that we have are just, let's just put them in this data. It's just a list of range from 0. It's just from 0 to n-1. So let's just say list of range of n. And now to find, for finding in a union find, we just check if the parent of x is x itself. If it is, then we are done. That we can't, that's the parent, right? Because in union find, the parent is the value for which its own parent is itself, right? So at that point we can, if it's equal, then we can just return it, right? Otherwise we look for the parent of its parent, because that's how union find work, right? Its parent is the parent of its parent, and we keep going until we reach the upper level parent. And so we do find of data x. And then for union, it's pretty straightforward. We just say the parent, we choose one of them, we make one of the parent of one of them be the parent, we make the parent of the parent of one of them be the direct parent of the other one. That's how it works. So we just take the parent of one and make it the overall parent, essentially, right? Okay, so now we'll go through the edges in connections, and we will find the parent of u, the parent of v, as we said in the overview. So we do that like this. And then we check if they are different. That means they are not yet in the same components, but here they share an edge. So that means they are in the same components, so we need to union them. Otherwise, they have the same parent. So they have the same parent. So in same component, which basically means that they are in the same components, right? But there is an extra edge that an extra edge that they share, right? And so here that means that we have an extra edge, so we need to count that, right? So we count the extra edge, and once we are done here, we can know the number of connected components. And so to know that, number of components is just the length of all the parents of the sets, right? And so to find the parents of the sets, that's just the, so we put them in a set to get the unique ones. And so the set here is, so for each node in the range, we find its parent, and because we are doing set, we get unique ones, and so we will get only the unique representations of components, which will give us the number of connected components. And so now we can do the check. If the number of extra edges, so extra edges, if that's less than the number of components minus 1, so this is what's required to, so this is required lengths, right? So this is the lengths that we need. So if the number of extra edges is smaller than those, that means we can't connect the components. We can't connect the entire network, so we need to return minus 1. Otherwise, that means there are enough extra edges, so we can just return how much we need. So we need the required number of lengths, right? And that's pretty much it. So let's run this. Yeah. Okay, let's submit. Okay, so this solution passes. So one thing we can notice here though, so there is another way to solve this one. So it's actually, we don't need to count the extra edges. Why is that? Because the extra edges here, we count them so that we can return minus 1, right? If we can detect if we need to return minus 1. If we don't, so that we can detect that we don't have extra edges. But actually we can do that easily with just, here we can check if the length of the connections is, so if the length of the connections is less than n minus 1, so we know that for a graph, the number of nodes, the number of edges needed to connect the entire graph is n minus 1. So we know that, right? We have n nodes, right? In order to connect all of them, we need n minus 1 edges. So if we have less than those, that means we certainly don't have extra edges enough to connect all of them, so we can return minus 1. But otherwise, if we have either n minus 1 or more, then by definition, one of them, the rest that are not the n minus 1 edges needed are that are not connecting to other nodes. They are connecting the same nodes multiple times, right? So we don't need actually to count extra edge. We can just say, okay, if we don't have enough edges, return minus 1. Otherwise, now we just need to find the number of unconnected things or unconnected nodes, or the number of unconnected components, and we can just return that minus 1, right? Because in order to connect those unconnected components, we just need to get the number of them and do minus 1, right? Just by treating the components as if they were nodes, in order to connect 3 components, we need 2 nodes, right? We need 2 edges, right? And so that's what we use here. So we will keep this the same, except we don't need to count the extra edges. So we can remove this. We still do union and find to get the connected components. So now we know the number of connected components, but now we don't need to check this. We can just directly return the required lengths, and that is just the number of connected components minus 1, and that's pretty much it. So if we submit this, it still passes, right? So now though, well, we actually have another way just to show you another way of doing it. We have another way of counting the number of connected components without doing union find. Union find is a little bit complicated because yeah, we are not used to implementing it, so maybe it's a little bit complicated, but we know how to find the number of connected components using DFS, right? And so we could just use DFS here. And so in order to use DFS, let's just keep this because this is needed. It allows us to know if there are enough extra edges or not. But here we just change how we compute the number of connected components. So how can we do that? So we can just construct a graph and do DFS, right? So we need a graph and we need the number of visited nodes. So our graph would be a dict of either a list or a set. I'm going to use a set here to have only unique edges. And that's the visited set. And then I will go through the connections. And basically, since it's an undirected graph, we'll add for u the node v, and we do the reverse. And now we can start doing DFS. So our DFS that will count the connected components. And so DFS starting from a node, we'll check if the node is invisited. Well, this is not a connected component because it's already included in another connected component that will be counted separately. So we need to return 0. And then we need to say if it's not invisited, then we need to add it to the visited because we just visited it by calling this function. And we need to go through its neighbors and call DFS on each one of them so that this all forms one connected component, right? And we'll return 1 because this forms one connected component starting from this u, right? And here we need to call DFS on every node and then just get the sum because any node that was already included in another connected components will be skipped here with this return 0. So getting the sum will give us the unique connected components. Or you could do it differently here, which means let's just initialize the number of components like this equal to 0. And we could say for I in the range of, so these are the nodes, right? Range of n. Then we can check if, then we can just call DFS of I, and then whatever result we get, we add that to the number of components, right? So if I was already included in a component, we'll get 0 because it's already visited. If not, we'll get 1, and it will be, all those that are connected to it will be added to visited, so we won't count them again. And that's pretty much it. We'll return the components at the end. So let's run this. So here we make sure we have enough extra edges, and we count the number of unconnected places, which is just the number of components, and just we return their number -1 because that's the number of edges we need. And so we submit here. Okay, so this passes. A slight small modification that we may want to do here. This is not really necessary, so we can just do the sum of DFS of I for I in range of n. This does the exact same thing and should give us the same result. Okay, so that also passes. Yeah, so these are 3 different ways to solve this problem. Yeah, so that's it for now. Thanks for watching and see you next time. Bye.